Hey guys, hi, this is Radhakrishna. Welcome to my channel, and today's video is going to be about how a satellite actually goes through its operational life cycle. As in, if a satellite is there which is observing the earth, how do you command it to look at Delhi, and it magically looks at Delhi and sends you back the data of Delhi. So this video is actually going to delve into all of these things. I mean, what actually comes in between this cycle of look at Delhi and oh, here is my Delhi, right? So this is going to be the context of this video, and it's also going to be very theoretical. I'm not going to go into the depths of the mathematics, but as such, just to know what actually happens. All right, so before going into the operational complexities, it's important to understand what actually a satellite is trying to do. And in most of my previous videos, I hope you already answered that, but to just give an introduction, most of the satellites do something called as remote sensing, right? The satellites other than the navigation satellites or the satellites which are data transfer satellites, most of the satellites do remote sensing. I mean, they try to sense some parameters of objects remotely. I mean, they are at a certain distance, and they're then trying to look at an area as a whole, right? And then most of the times, this thing that they're trying to sense is electromagnetic radiation that's coming off of a body, or the satellite itself is sending some electromagnetic radiation and it is measuring the reflected electromagnetic radiation back. All right, so most of the time it's going to be both of these cases. And if a satellite, you know, sends its own radiation and emits and observes the reflected radiation, it's called as an active remote sensing. All right, or if a satellite is observing the radiation that is coming from another source from the object, it's called as passive remote sensing. And when I speak of the electromagnetic radiation can be in any of the bands of the spectra of light. All right, so in the normal days, or in the normal life, what we observe is an RGB spectra. In our smartphone cameras or DSLRs or point and shoot cameras, we have RGB. All right, so how does this work is basically we have three different bands, and the photons that are coming over are only observed in these three different bands, and all the wavelength is not observed. And then from the information that we get from these three different bands, we mix all of these three different bands, and then we are able to see a color image. And this is all is required if you want to see somebody in a color image, or if you want to see somebody through your eyes. All right, but there is a very big world, a very big spectra that you are not able to see through your eyes. And most of the time, the information, if you're not able to measure in those bands, you're not able to get what you want. And that is why we have different sensors in different parts of this electromagnetic spectra. So just to give you an example, what I'm going to do is I'm going to show you these bands in the increasing order of their energy. All right, and our bands are here, R, G, B, or generally in India they teach you VIBGYOR, right? So your VIBGYOR is going to be this way, VIBGYOR. So this is in the increasing order of the energy. This is violet and this is red. So the wavelengths that are going to come after the violet color are called ultraviolet. Ultraviolet, that means they have energy more than the violet rays. And then the wavelengths that are going to be on the left side are called infrared. Infrared meaning the energy of this rays is less than the red, infrared. And then you have your microwaves or radio waves here, and then you have X-rays and gamma rays here. All right, so this is the spectra of electromagnetic radiation, and you have your sensors all over the spectra. All right, you have infrared telescopes, you have ultraviolet telescopes, you have X-ray Chandra telescope, you have your normal telescopes in RGBV, you have microwave observatories, and you have gamma ray detectors or gamma ray telescopes. So all of these sensors are given. Now the thing is, whenever you plan a satellite, you need to be observing a body, may it be moon or sun or earth or any other planet or any other thing in most of these or any of these electromagnetic spectra, if it is light that you're measuring. All right, So for the purpose of this video, I'm going to be taking a small example that I'm going to be observing my body or earth, for example, in RGB wavelengths. So just imagine that you have a point and shoot camera which is made with space grade electronics, and then you're taking it to space and it works because it's made of space grade electronics, and then you're able to capture different cute pictures of Earth. And yeah, that's it. So your images are going to be the satellite images. They're not going to be as good because of your implanning that goes on in and around your point and shoot, but yes, they're going to be the satellite images. And yeah, so that's what satellites do. They take images, or they sense some parameters. In this case, it's going to be the reflected sun rays that your point and shoot is capturing. All right, so that's all about it. But the most important thing here comes when you are not with the camera, right? There's just this camera floating around in space, right? So this is almost like an autonomous driving car. So it has to almost drive itself. And then some other day you told that you need an image of Delhi because maybe you want to see its urban growth, or maybe you want to see the flow of the rivers in and around, or maybe you want to do something, right? So you wanted image of a Delhi city. And then how do you talk to the camera to take the pictures of Delhi? So this video that going to be followed after this is going to be trying to explain that part. So the most important thing in the satellite operations is called NGC, and this is not National Geographic Channel, by the way. It's navigation and yes, guidance control. And one cute little joke that I wanted to tell was I was looking through the footage of Chandrayaan 2's landing event, and I was very curiously observing that tele show that was streaming from his track. And then I get a message in WhatsApp, right? I get a message that NGC is looking through the satellite data, and they will analyze, and then they will get back because the lander's communication is lost. And then Nietzsche, my friend writes that, what is this NGC? Is it National Geographic Channel? And then I'm done with it because that's supposed to be navigation and guidance control. All right. So this is a very complex part of a satellite's operation. So there is this two parts. You have your payload or a camera or a sensor, and that is actually controlled by this navigation and guidance. So what happens here is, but first let us try to understand what is navigation and what is guidance, right? So navigation is something you can call as self-awareness. So you being aware of your location and your state in this three-dimensional space, and that is navigation. So for example, when you're going out in oceans or seas or rivers, or for example the land, how do you know where you are? Currently on Earth, everyone uses GPS, but when there was no GPS, people used to look at stars, or people used to sense these westerly winds or the wind direction with respect to time or the seasons. And then they know, okay, I'm at this point on Earth, or I'm at this point in time, right? So something like that. So that is called as navigation. And then you have guidance, which says, how do I proceed to move if I have to be at that particular state in the future? So this is called as guidance. So this is future movements or future planning of how do I go about what I have to do. And having a control on both of these is the navigation and guidance control system. Alright, now let us understand what happens in a satellite's day-to-day life. Okay, so for understanding that, we have to understand some parts of this navigation and guidance. So what are some of the instruments that I'm going to say on how do we get our navigation and guidance, right? So for example, how do we so for any navigation, I said that I have to know my location, I have to know my state, as in my rotations and velocities and accelerations. All right, and then I have to know all of these things in order to say, okay, I'm at this particular point in space. All right, so how do we know our location, or how does a satellite in space without a man sitting inside it know its own location? Okay, it's almost similar to how you know your location on land. It's mostly using GPS. Okay, so the satellite in space also can look at this GPS satellite sending their own time signals, and then it can track its own location. Other than that, you can also do a ground-based ranging. So what happens here is there are very big ground observatories or ground radars. Okay, and then they send these huge radio waves, radio pulses. Those get reflected out of satellite, and then that reflected pulse comes back, and then you try to calculate, okay, then there's this object roughly at around where I predict my satellite, so this is going to be my satellite, and its location has changed this much, so its new location is this, and this is going to be the predicted orbit or the changed orbit. So you do this calculations on ground, and again you tell to the satellite, okay satellite, your position has changed so and so, your velocity has also changed so and so, please take care of yourself. So this is how your satellite's location is done, on board using GPS, off board or offline using ground-based rangings. So how do you calculate then your velocities? This is by differentiating your position vectors in space. So you know your positions, thereby you know your velocities. If you know x, y, z, x1, y1, z1, you know you can get x1 minus x by t, so that's going to be dx by dt with the velocity in x direction, so on for the velocities in the y direction and the z direction. Other than that, you also have accelerometers on satellite, which give you its own accelerations with respect to time. So there is this concept called as dead reckoning, if you've ever heard of it. So this comes about when you're learning some navigation courses. So what happens is that you are going in ocean, just an example that you're going in an ocean, and then your GPS location suddenly cuts down. You're not getting, your GPS is not working. So how do you calculate where you're going, right? So the thing is, you know your last position of the GPS, and then you calculate your own velocity, so the distance that you travel from that point in time, right? So my last location was this point, and then I moved x1 meters in x direction, y1 meters in y direction, and z1 meters in z direction. So my point or new location should be last position plus this moment. This calculation from the last position using the new moments that you calculated, it's called dead reckoning. Dead reckoning is a relative location calculation with the last updated time. So your sensors are actually dead, so you're just able to calculate brute force calculation, whatever you were able to do to just understand where you are. It's called as dead reckoning. So accelerometers help in that. They help you integrate your velocities, and then integrate that to a final position movements, and then just estimate on board how much is my position now. So you get this multiple data from accelerometers, and then you get a location, you get from GPS a location, you get from ground a location, and there are different sensor fusion algorithms that run about to calculate the most accurate location of a satellite. So that's how satellite knows, okay, I am here. All right, now more important than location is the direction or the rotation of how a satellite is. Also, it's called as attitude of a satellite. It's almost similar to an aeroplane, for example. So just let me draw an aeroplane. Okay, so this is just an aeroplane's diagram. So you have your aeroplane, and it always has to be this way. For example, my satellite has to be this way because my camera is here. So my camera is here, so it is looking at Earth. Alright, if my camera is upwards, it cannot see. If my camera is somewhere looking in space, it cannot see right? So always my camera has to be pointed where I have to look at. Alright, so this is also a very important concept or very important part in how we use a satellite. And there are different angles. Basic rotation I'll tell you. So if this is an aeroplane, if you're rotating it this way, or in the movement of flow or movement of the object, if your object is moving this way, if I am using that as a rotation axis, this movement, right, this movement is called as a roll. Okay, so if my object is moving this way and if I use it as an axis and rotate it, this is called as a roll. Okay, and if I move it up and down this way, okay, this way, it's called as a pitch. And what is the axis that you do? The axis is this axis. So if I am moving this about this axis, it's called as a pitch. The movement is going to be pitch, and my yaw movement is going to be this. My yaw movement is going to be that. And for the axis, that axis is going to be this axis. If I do a rotation, it's called as a yaw movement. And by combination, a certain combination of a roll, pitch and yaw, I can bring this aeroplane or a satellite into whatever configuration I want to, right? So these are these three angles. Maybe also you can call them as Euler angles, and you can just use a standard rotation matrix. So for example, if your initial coordinate system was in XYZ, and then you have this rotation matrix filled with these angles or cos, sine, there is this standard rotation matrix that you use to convert this frame into a new frame, the rotated frame, x prime, y prime, z prime, and then you do your calculations in the new coordinate frame. Alright, so this is the basics of rotation, and then knowing these angles is also important. And just imagine, how do you calculate these angles in space? With respect to what do you do? GPS can tell you rotation, and ground-based rangings can't tell you location, because your cross section is almost going to be similar. Listen, until you have a big peak or in some direction, and the cross section of your satellite is not going to be that huge. There's small research that happens even by saying rotation, but it's insignificant. Other than that, you need to know rotation very accurately, and there are different attitude sensors that can give you your rotations. There are gyroscopes which can give you the rotation. If you are interested in learning about gyroscopes, there are different kinds of gyroscopes, but then the basic principle of most of the gyroscopes is the conservation of angular momentum. And I am sure that you might have come across this experiment or the demonstration that a cycle wheel, when rotated, it is hard to move its direction. That is because the angular momentum is already there, and if you want to change the angular momentum, you need to give a torque, right? And so that itself is the principle behind this gyroscopes. Alright, so the gyroscopes can be used to measure rotation. But other than that, the interesting thing in most of the satellites is they use something called as a star sensor to measure rotation, or the attitude, for example. So how the star sensor actually works is almost similar to how our primitives or ancient people used to navigate the wide oceans. It's by looking at stars. And this is a very interesting subject personally for me, because I'm in awe of understanding how beautiful our life is just by looking above, right? For example, the basic star to know about when you're doing a navigation through stars is Polaris. Polaris is a star which is very close to the North Pole. Alright, so I'm sure that you might have seen these star trails images. Alright, so the star trails are like this because the Earth actually rotates. The stars do a trail because stars actually move in a circles. But the one point that does not show the star trail is the North Pole, because our rotation axis of the Earth goes through the North Pole. The rotation in and around that point is actually very minimal, and Polaris is actually very close to the North Pole, and that is why that star does not actually move or rotate in space. And if you are able to detect Polaris, that means you are able to tell north direction, the celestial north direction. And I can tell my south, and I can tell my east and west, similarly based on the rising and setting of stars or certain stars. And other than that, if you want to know at a latitude or longitude on Earth where you are in, you track some stars, and then there is a detailed position table of stars with respect to time. So at this particular time of the day, if my star is at this particular location in space, then what you're observing it, that the point is this particular point. All right, so there is this position charts that you have, and from these positions of the stars you can actually derive your location on the Earth. And if you're able to locate yourself on the Earth, it's possible to locate anywhere in the space, and that is exactly the principle behind the star sensors. Okay, and the star sensors, what they do is they use a detailed map of the stars, or quasars for that matter. So there are these particular stars whose location actually never changes, and we know the location very accurately. And there are these patterns in sky all around us, all in the northern hemisphere and the southern hemisphere. We have a detailed compilation of more than 3,000 patterns of stars. And then all your star sensor has to do is look at a certain patch in sky and take its image and correlate this image in all possible rotations with the database that you have. And somewhere or the other you gonna get a correlation, and then you know that these stars are there in your particular photo, and then you try to correlate the angle. All right, so you correlate the angle, and then you know, okay, with this particular rotation of the image, the stars are getting correlated with my database, and so my rotation in space with respect to the celestial north and south and the east and west is going to be this angles. Right, how beautiful it is. And so this star sensor is able to give you the rotations. Even the gyros are similar to accelerometers for determining location. Gyros give you rotation with respect to one point in case of dead reckoning, but to know absolute rotations in space, it's going to be the star sensor that's going to give you the rotations. All right, so using the star sensors you get rotations, and using the gyros you get the rate of rotations, or for example rotations itself you integrate with time, and then accelerometers and location. So now that you are self-aware of where you are with help of all these awesome sensors, what you do is, okay, I'm at this particular point in space and time, and I'm in the influence of Earth, which is gravitationally pulling me, and so I'm bound to it, and so I can predict my orbit. But there is a lot of molecules even in that atmosphere which is going to affect my orbit, and my orbit is unpredictable. So I need to be able to maintain this orbit. So what I do is a set of guidance commands. Alright, so what I do is I fire myself to have this particular velocity at certain points in space and time, so that I maintain this orbit. So for doing that, we calculate satellites' loss of the velocities and everything, the orbit predictions and all, with certain sampling intervals. And then if the satellite loses too much velocity, or if the satellite is deviating too much from its orbit, we send up a certain commands which actually able to move the satellite forward, or accelerate it, or increase its velocity, or rotate it. So these are a set of guidance or a driving commands, for example. Alright, so how do you do this generally is using propulsion systems. Alright, for example, if I have my satellite here and I have 3 propulsion systems here, and this is a very basic example. So if I am able to fire one thruster this way, this thruster, if I am able to fire, my satellite is going to move forward. And this can increase its velocity. So by doing a set of fire commands, and for a certain length of intervals, I can maintain my orbit. But what about the rotation? Alright, for example, if my camera is here, alright, and I am moving like this, and my Earth is here. If I moved here and still my camera is looking like this, it's not going to look at Earth, it's going to look at some space in Earth, or in some space. So I have to rotate my satellite this way again, so my satellite is like this. So how do I do that? So for a basic rotation you need a torque, and the torque is a force which does not move the which does not induce a linear motion. How do you do that? Is basically by putting a force away from center of mass. Alright, so this force was going through center of mass, but this force does not go through center of mass, so it induces a torque. So for example, if you can see this, if I am putting my force here, this is going to move, but if I am putting my force here, it is rotating, right? It is rotating. So that's basic concept of torque. And so if I'm firing only one thruster, I'm going to rotate this is going to move this way, so I'm moving this part this way and this part this way, so it's going to get rotated. Alright, so this will get rotated this direction, so I have to fire this thruster to rotate this side, and so that's how you do a rotation. So there's this calculations that you have to do. For example, now coming to the final case, or if you want to observe Delhi, what you have to do is you have to calculate a state S0 of a satellite at a time t0 that you want to observe, and you take it through a detailed procedure of guidance commands, whether the guidance by the instruments that are present on the satellite can give you a state S0 and at a time t0 if it can give what are the series of those commands. If your function results in a set of commands, what you do is you take these commands and then you uplink that to your satellite, and then the satellite executes each of this command at a point in time that you command it to, and then all of those commands are executed, and at a time t0 your satellite is a state S0 which is observing the Earth. Alright, so this is how navigation and guidance actually happens in the satellite, and all of this is actually very complicated. I mean, I told all of this to you in a very simple manner, but there is a lot of different mathematics and engineering that goes on in the behind, and there are a lot of validation tests for each of the subroutines that are in here, and a lot of different hard work is done for preparing those awesome instruments, the star maps, and the testing procedures that have to follow, and the analysis that comes out after a certain guidance is happening. And oh my god, this blows my mind itself. So this is a huge topic, and this is actually the crucial thing. Maybe for a launch vehicle also the same thing happens, and then for the satellites and any spacecraft for that matter. I hope all of you have learned quite a few things from this video, and for coming up like more like this videos, you like my video and share and subscribe to my channel, and then you will always be notified if a certain video comes in. And I promise that there are a lot of videos that are going to come in which are having some interesting stuff like this. So meet you in my next video, guys. Goodbye.